In this video, we'll start our introduction to organic molecules, how we represent organic structures, and we'll get into naming straight alkanes and simple branched alkanes. So for organic molecules, there's going to be compounds that contain carbon. These, of course, have many important applications, so pretty much every molecule that you encounter in biology that are making up the organisms are going to be some type of organic molecule. They're also very important for plastics and polymers. They're the main molecule in petrochemical fuels, and also they're important for making pharmaceuticals and different types of drugs. Okay, so let's talk about how we represent these organic molecules, because they tend to be actually very large, since every carbon can form 4 bonds, and so you can make some pretty long chains for these. So let's look at how we'd draw them with how we'd normally draw a Lewis structure. So here we have one with 6 carbons and 14 hydrogens. The Lewis structure would look something like this if we drew it based on our normal rules. So we have our 6 carbons and hydrogens attached to all of them to form an octet. If we wanted to use our rules for geometries and draw the 3D structure, we could see it's still the same bonds here, but we can see sort of the bond angles. Since all these carbons are going to be forming bonds with these hydrogens and the other carbons, these are all going to have a steric number of 4, so these are all going to be sp3 hybridized carbons in this case. And so these angles will all be about 109.5 degrees, so you can represent them this way. We've also seen a little bit of these compounds being represented in these condensed structures. So instead of drawing all the bonds in, they're kind of implied by the way we write the formula. So for each sort of unit, that is one carbon that's attached to the other. So this would be the first CH3, and then this CH2 would be this C with its 2 hydrogens attached to another CH2, and so on and so forth. And then we end with the CH3 at the end. Okay, so when we're writing the organic molecules, we actually use even a more shorthand representation for these, where we can both show the number of carbons in the compound, but also represent a little bit of the geometry in it. And this is the line angle structure. Essentially, for the line angle structure, for now while you're practicing, what you can do is you can take every carbon and sort of represent it by a dot. So let's take this 3D structure here. We have the 6 carbons, so that would be like 1, 2, 3, 4, 5, 6. And then we'll connect all of them with the bonds that are connected between the carbons. And what we don't do is we don't draw on the hydrogens. Since organic molecules are going to be focused around carbon, these are all going to be in the second period. So pretty much every organic molecule is going to obey the octet rule, and definitely the carbons. So unless there's something special in the structure, we're assuming every carbon, represented by these lines connecting the dots, is going to have an octet, and anything that's not written, it's implied that that's filled in with hydrogens. So the line structure would look something like this. Once you get the hang of these, you won't actually draw the dots first. You just start with the lines. So if I was going to draw this structure, we know this has 6 carbons, so I'd start with 1, 2, 3, 4, 5, 6. And that would give us that same structure. And all the hydrogens, again, are going to be implied. Okay, so let's look at how this will save us time on a more complicated molecule. So here's one with the condensed formula CH3, and we have 3 of those. So 3 CH3s connected to a carbon, connected to an oxygen, connected to another CH2, and another CH3. If we were to draw the Lewis structure, that would look something like this. So here's our 3 CH3s. Connected to the CO, and then the CH2, and another CH3. If we were to represent this in a line structure, it would look something like this. So this is much more simple than that Lewis structure. I'll talk through how I would write this line structure again, just to give an example for all of these. Okay, so going back to this, we have 3 of these CH3s, so 3 carbons attached to the carbon that's the oxygen. So here's 1, 2, 3 attached to this carbon that's attached to the oxygen. And we are going to draw in every element that's not a carbon. We only leave hydrogens off if they're bound to just a carbon. So we're going to draw in the O. And then we have that connected to a CH2. So there's a carbon with 2 hydrogens and then a CH3. And so that's how we get that compound structure that we drew up above. As a reminder, in these line angle structures, we do not draw the hydrogens that are bound to carbon. So our first class of organic molecules we're going to talk about are alkanes. So alkanes are saturated hydrocarbons. A hydrocarbon is a molecule consisting only of carbon and hydrogen, so nothing else. Organic molecules can have other elements, they just have to have carbon, but a hydrocarbon will only have carbon and hydrogen. A saturated hydrocarbon contains the maximum amount of hydrogen atoms. What do we mean by maximum amount? It comes from this formula here. So the formula is however many carbons you have, we're going to set that number to n. For the hydrogens, in order for it to be saturated, you need to have 2 times n plus 2. Here's some examples. So CH4, this is called methane. We'll talk about that in a second. The n is equal to 1. And so 2n plus 2, so 2 times 1 plus 2, is equal to 4. So 1 carbon, 4 hydrogens. Here's a couple of others. So here n is equal to 4. This is C4H10s. This would be butane. And we have the number of hydrogens is equal to 2 times 4 plus 2. So it's equal to 10. That obeys the rule for saturated hydrocarbon. Here's another one where it's also C4H10. So it still follows the same rules. But notice the structure is a little bit different. This is an isomer. We have the straight chain alkane, this one where the carbons are all in a straight row. Or we can also have it in branch chain where things don't all follow a single line. So in this case, the carbons, right, form this shape. But we still have 4 carbons and we still have 10 hydrogens. So these are both saturated hydrocarbons. These are both alkanes. So talking about some of the properties of alkanes, they're all going to be nonpolar. Remember, these carbon-hydrogen bonds have a pretty small electronegativity difference. So all the individual bonds are nonpolar, so the molecule overall is nonpolar. Because they're all nonpolar, the only intermolecular force is going to be dispersion forces. And so these are fairly weak, which means they'll tend to have lower boiling points, but they also follow the rules for dispersion forces. As they get bigger, they're going to have a higher boiling point. And if the chains are more branched, remember that these molecules can't stack as close together. So like the dispersion forces, the force won't be as strong with a branched molecule, and so it'll be a lower boiling point. So we can look at this with these 3. Methane has a very low boiling point, negative 182 C. For the 2 compounds that we showed you with the 4 carbons, the one that is less branched has a slightly higher boiling point. They also tend to be fairly unreactive, although they're also very combustible. So a lot of the fuels include a lot of these straight alkanes. So they're pretty combustible, but they don't react with a lot of different types of molecules to make different molecular compounds. Okay, so for naming these straight chain alkanes, we are going to use a new set of prefixes. The prefixes are going to refer to the number of carbons. So this is the list of the prefixes that we'll use for straight chain alkanes. So if it has 1 carbon, it's going to be meth for the prefix. If it has 5, it'll be pent, so on and so forth. After we name the number of carbons, we just add ane to the end of the word to tell us what the compound is for that straight chain alkane. So methane would be 1 carbon, and that's it. Since it's saturated, we need to have these 4 hydrogens. Something like pentane would be 5 carbons, so that would be 1, 2, 3, 4, 5. We'll leave off the hydrogens, so that would be the structure for pentane. Here's the examples again. So we have methane, there's the butane that we talked about, and we can look at this structure. So if we wanted to go in reverse and think about how we name this, we could count the number of carbons. There are 9. So we'd look at the prefix and see that this would have to be nonane. We can also have the branched alkanes. So again, these are going to be isomers of straight chain alkanes. So for this one, the C4H10, we know that is butane. How do we name this branched chain alkane? Well, we can't call them both butane because we saw they have different boiling points and they actually have a few other different chemical properties. So we can't name them exactly the same. We need different names to avoid the confusion. Like the naming we did with the inorganic molecules, not only do we have to call them something different, but we want to use a systematic naming system so that we know how to name any molecule, even if we make a new one. And we want it to be unique for every type of molecule we could possibly come up with. So again, we have a list of naming rules that we use for these organic molecules. So the general idea for the organic molecules is identify the parent. This is going to be the longest chain of carbons. Then we'll look for substituents. This idea of substituents is very important in organic chemistry. These are going to be things that are bound to the parent chain. So anything that's bound to carbon other than an H, so other carbon chains, and then we look at functional groups, even other molecules, and then we'll determine the position of these substituents and use that in naming. So let's look at the parent chain in these compounds. So here we can see the longest chain of carbons is going to be 1, 2, 3. Even if we go the other direction, it's still just 3 carbons. For this compound here, we can look, if we go this direction, we have 1, 2, 3, 4, 5, 6. And if we go this direction, we have 1, 2, 3, 4, 5. So our longest chain in this case is going to be the one with 6 carbons. So when we're naming these compounds, we'll name the parent based on the number of carbons in the chain, and then we'll add ane to the end. So the parent molecule in this case would be propane, and this one with the 6 carbons, what do you think the correct name would be? Yeah, so that's correct. In this case, it would be named hexane. We'd use the prefix hex for 6 carbons in the parent chain and then end it with ane. We'll then write the substituents before the parent chain. If the substituent is an alkane, the substituent name will be the normal prefix and we'll add this YL suffix to it. So we can see for both of these, the substituent both has 1 carbon. If we look at 1 carbon, that would be meth. And with the prefix, that would be methyl. So if we look at this compound here, for the methyl group, really, there's only 1 place for it, so we don't need to worry about it too much. But we could see for this chain here, we could have this methyl group attached to this carbon. We could attach it to this carbon, etc., right? And they'd all be different. So we need some unique way to name where that methyl group is attached, and we do that using numbers. What we'll do is we'll count the carbons, and then we'll minimize the location number for the substituents. So in this case, here we're starting with 1, 2, so this would be at the 2 position. That's really the only option in this case. For the longer hydrocarbon, would start here, 1, 2, 3. So the 3 position, we can double check to make sure that's the shortest. If we count this direction, we get 1, 2, 3, 4. So 3 is going to be our shortest one for counting for the longer chain. And then we'll write the location number before the name of the substituent when we're naming the compound. So the full name of this first molecule would be 2 for the second position, methyl for the methyl group, and then propane because that was the parent molecule. For the second one, it would be 3, again the position, methyl for the methyl group, and then hexane for the parent molecule. So we have 2-methyl propane and 3-methyl hexane in these 2 examples.